Okay, now, hopefully, we're on top of this. And I really, incidentally, generally did have an R in it. That caught my eye a minute ago. But anyhow, instead of R and delta R, of course, since we're integrating along a position along the x-axis, I should have used x and delta x. And we can then say the force at position x is what? Well, we never wrote it out here, okay? But we're going to have our 9 times 10 to the negative fourth Newton meter squared in the numerator, since we still have the two charges. And then we just have to divide by x squared instead of x squared plus y squared. And our unit vector will just be I, so we don't have to worry about dividing by the square root of x squared plus y squared. We'll just divide the xi by x and get I. So force is going to be our 9 times 10 to the negative fourth Newton meter squared over x squared times I. Now technically, we need to do a dot product, force versus displacement. If we do that, our displacement is in the I direction. Well, okay, we're actually doing the integral, and since everybody here has had multivariable calculus, I'll write it out this way. If anybody's watching that hasn't had multivariable calculus, it'll be pretty obvious what we get. But writing it out in all its rigor, we're going to have our 9 times 10 to the negative fourth Newton meter squared divided by x squared times I, dotted with our displacement increment, which is dx times I. Of course, this just gives us the scalar integral 9 times 10 to the negative fourth Newton meter squared over x squared dx, which is then 9 times 10 to the negative fourth Newton meter squared times negative 1 over x, antiderivative of the reciprocal of x squared, and that'll be evaluated from 0.1 meter to 1 meter, and that equals what it equals, right? Okay? So you're going to have, well, it's going to be negative 9 times 10 to the negative third joules minus negative 9 times 10 to the negative fourth joules. Hopefully I did that right. I'm doing stuff in my head, that's always dangerous. Okay? Which is going to be negative 8.1 times 10 to the negative third joule. Now, when we did the area here, we weren't worried about directions and so forth. We just found the area under the force versus position curve, right? And, uh-oh, something's wrong here.
Yeah.
Should be backward. It
Yep,
should
yep,
be
yep.
backwards.
We evaluated this limit, so that should be the negative of the negative, and this should just be negative. Okay? Okay, so the force does work, positive work on the charge, which would tend to increase its kinetic energy, which is exactly what happens if you bring two repelling objects close together and just release them. And we did that with magnets and cars, early in our first semester course, so you have experience of that kind of repulsion, right? And you know what would happen if you turned the magnets around and you had an attraction. Release from here, come back to here, you'd have the same energy you would if you had the magnet in the opposite direction, and speed them up with repulsion, right? Okay, so we have this. How does this compare with our estimate? Compares really well. That's 81% of this, isn't it? Okay? If I increase that to 10 times 10 to the negative third, well, that's what I have, right? Okay? So y'all wanted to divide by 16, I wanted to divide by 10. Turns out if we'd have divided by 12, we'd have been really close.